Hello, everyone. My name is Cameron Hicks, and for Physics 2 2212, this can be our Lab 2, which says charge tapes revisited. Unlike our previous lab where we treated each tape as a single point charge, in this experiment used a more realistic model where the charge is evenly distributed throughout the tape as many charge elements. The goal is to determine how much charge is required for one tape to float above another, and then compare our experimental observations with the predictions from the distributed model. By combining observation with computational modeling, we were able to test how accurately our physics model represents the real system. And overall, we found that our model closely matched what we observed, showing that electric forces can realistically counteract gravity. This lab is based on Coulomb's law, which describes the electric force between charged objects, and the magnitude of the force depends on the amount of charge and the distance between them, and it acts along the line of connecting the charges. And we also consider gravitational force, which pulls the tape the top tape downward, excuse me. And for the tape to float, the upward electrical force must equal the downward gravitational force, and then they would cancel out. And then to model this more accurately, we use the superposition principle, which means that the total electric force equals the sum of forces from all charge elements in the piece of tape. To simplify the model, we made several assumptions. We assumed that each tape had approximately the same amount of charge and that the charge was evenly distributed along its length. And we ignored air resistance and any motion effects since we focus only on the equilibrium condition where the tape is not accelerating. And we also assumed that the tape remained aligned and stable without significant rotation or bending. And our initial conditions slash measurements included the tape length of 0.2 meters, the estimated tape mass of 2 times 10 to the negative fourth kilograms, and the floating separation distance of 0.019 meters. And this is just our same observational data from the previous lab. Using two charged pieces of tape, we affixed 1 to 2 exponent markers, and then we held the other one approximately as it approached the first U tape charge over here. And then we found that when the two pieces of tape were near each other, the one affixed to the marker center raised a distance, signifying repulsion. In our computational model, we represented each tape as a series of small charge segments distributed evenly throughout its length. We calculated the total electric force by summing the conditions from each using Coulomb's law. And the distributed approach is more accurate than treating the tape as a single point charge because it accounts for how charge is physically spread out. And from our model, we calculated that the electric force is approximately 2.07 times 10 to the negative 3 newtons, and then the gravitational force is approximately 1.96 times 10 to the negative 3 newtons. When comparing our observations with the computational model, we see strong agreement. Experimentally, the tape floated, which tells us that the electric force was approximately equal to the gravitational force. In our model, the electric force is slightly greater than the gravitational force, which explains why the tape was able to lift and remain suspended. And then the small difference between the two values can be explained by experimental uncertainty and simplifications in our model. Overall, the agreement between observation and computation supports the validity of our model. And there are several possible errors in our experiment. Some of them include uneven or changing charge distribution, inaccurate distance measurements between tapes, air resistance or drag force affecting tape stability, charge loss due to humidity or handling, and tape not behaving exactly as point charges. And for the discussions and additional questions, first question was what was the magnitude of the charge on one piece of tape as calculated by the computational model? And we approximately calculated this to be Q, or the charge, equals 2.21 times 10 to the negative 8 coulombs. And then this does add up with the magnitude of the electric force being approximately 2.07 times 10 to the negative 3 newtons. And then what assumptions, approximations, or idealizations did we have to include in order for our experiment to work? And we had to ignore air resistance on a moving object and assume that each U tape that we made had the same amount of charge evenly distributed along the length of the tape. And in conclusion, this lab demonstrated that electric force can balance gravitational force, allowing a charged tape to float in equilibrium. By using a distributed charge model instead of a point charge approximation, we were able to more accurately represent the physical system. Our computational model produced electric and gravitational forces that were very close in magnitude, showing strong agreement with our observations. The estimated charge on the tape was realistic, and the model successfully predicted the behavior of the system. And although we made simplifying assumptions, they allowed us to analyze the system effectively without significantly reducing accuracy. Overall, this lab reinforced Coulomb's law and highlighted the importance of using more realistic models to better understand physical interactions. Thank you.